All right, so I've been a little bit backlogged on making videos for the Teams assignment, so I'm going to be putting out a whole bunch of them in rapid succession. So the first one is going to be over the exam 2 that I took in 2006. And so let's just kind of go through and solve these questions really quickly. So the first one says, a sign having a known mass of M is attached to the ceiling and a wall by 2 thin wires as shown. Each wire has essentially 0 mass and cannot be stretched. One wire is horizontal, the other is at an angle theta. Find the tension in each of the wires. Okay, so first thing that we want to do with a problem like this is to draw a free body diagram. We have our sign. This has some tension, we'll call T1, going up at this angle of theta. And then we have this tension we'll call T2 going to the left. And this has a force of gravity acting down mg. Now, in order to find these two tensions, or a system of equations that we can find the tensions, we need to draw a coordinate system. So we have, this is the y direction, this is the x direction, and we're going to apply Newton's second law. So that we can say that the sum of the forces is equal to mass times acceleration, which says that the sum of forces in the x direction is equal to max. Sum of forces in the y direction is equal to may. Now, because this is an equilibrium, this means that it's not going to accelerate in x or y. So both of these are going to be equal to 0. And so let's look at the sum of the forces in the x direction. So in the x direction, this is going to be T1 times cosine of theta minus T2. And in the y direction, this is going to be T1 sine of theta minus capital M G. Okay, so for our sum of forces in y, what we can do is we can solve for what T1 is. So from this equation right here, what we can do is we can solve for T1. It says that T1 is going to be equal to capital Mg divided by sine of theta. And in the second equation, we can solve for T2. So T2 is going to be equal to T1 cosine of theta, which is going to be equal to mg cotangent of theta when we take what we found in this equation and plug it in there. And so this is actually it for the first question. So we have our tensions that we were looking for in this problem. Okay, so we're going to move on to the next question. So in question number 2, we have these two blocks that are up against each other. So this says 2 boxes are at rest on a frictionless table. There is no friction between the 2 boxes. The box with mass MB will be crushed if a force is applied to it that has a magnitude greater than the known value TC. A force of magnitude P is applied to the first block, mass MA, at a fixed angle of theta. What is the largest value that P can have without the second box being crushed? And then we want to find the maximum value that P can have without crushing the box. If now the surface of the table is such that there's a coefficient of friction mu between the table and the first box, but all other surfaces are frictionless. Okay, so what we want to do with this one is, just as the other question, we want to draw some free body diagrams. So we have our mass MA here. This has some force of gravity, MA times G. We have some normal force, we'll call this N. We have the force that we're applying here, which is going to be P at some angle of theta. And we also have a normal force that box B acts on box A. So this is going to be NB acting on A. Okay, so there's no friction between the boxes, and we're assuming that there's no force of friction anywhere else. Okay. Okay, so the next thing that we can do here is we can draw the free body diagram for the second box. So for the second box, we have some normal force NB. We have MB times G, our force of gravity. And then we have the force that box A acts on box B. So this is our mass MB. This is the normal force that A acts on B. Right? So remember, when we're talking about normal forces, these are contact forces that are perpendicular to a surface. So that is our second box. And we can draw some coordinate system here. Okay, so this is going to be y, this is going to be x. Now, the next thing that we can do is we can set up a system of equations that we can solve in order to find what p can have as a maximum value. So what we can do is we can say that let's look at box A first. So sum of forces is equal to mass times acceleration. Sum of forces in the x direction is equal to ma times ax. This is going to be equal to p times cosine of theta minus nba. And then we can sum our forces in the y direction. So this is going to say that this is going to be na minus ma times g minus p sine of theta. So this one is going to be equal to 0 because it's not accelerating in the y direction. And so this says that na is going to be equal to m sub a times g plus p sine of theta. Okay. So now what we can do is we can find what the sum of the forces is for the second box. So sum of forces for B is going to say this F vector is equal to MB times A. And so this sum of forces in X is going to be equal to, just this force that block A acts on block B. So this is going to be NAB, which is going to be equal to MB times AX. Okay, and so then the next thing that we can do is we can find what the sum of forces in y is. So this is going to be sum of forces in the y direction is going to be equal to NB minus MBG, again equal to 0 because this is not going to accelerate in the y direction. And so this says that NB is going to be equal to MB times G. Okay, so let's put a box around some of the things that we know here. Know what normal force A is and what the normal force B is now. The next thing that we want to do is we want to look at our equations in the x direction. So we look at this equation, look at this equation. We can actually just add these together so that we can find what the acceleration of the system is going to be. So this is going to say that P cosine of theta minus NBA is going to be equal to MA A sub x, and then NAB is going to be equal to MB A sub x. Now the reason why I'm going to add these together is because I can cancel what the normal force is between the two boxes. This is an internal force, so ultimately Newton's third law is going to say that it's going to be equal and opposite. Those are going to cancel. And so what this says is that P cosine of theta is going to be equal to MA plus MB times A sub x. Okay. So now what we can do is we can find what the acceleration of the system is going to be by just moving this MA plus MB to the other side. And so the acceleration of the system is going to be P cosine of theta divided by MA plus MB. Okay, so that is the acceleration of the system. It's always a good thing to be able to find. But that's not actually what we're interested in. What we're interested in is the maximum value that P can have without the second box being crushed. Okay, so this puts a condition on the force between A and B. So what this is saying is that NAB is going to be equal to this critical value that we have here, which is also itself going to be equal to MB times AX, right? Because the force in the x direction acting on box B is always going to be equal to MB times AX. So the acceleration might change, but there's only one force acting in that direction. We can look at the free body diagram. It's only ever going to be this force. And so then we're putting a constraint on this and we're saying, okay, well, that force is going to take on a maximum value. What could the maximum acceleration be? But we have some expression for the acceleration. So we can take this acceleration that we have here, and we can plug it into this equation. And so this says that Tc is going to be equal to mb over ma plus mb times p cosine of theta. And now we just solve for p. So solving for p, we end up saying that this is going to be equal to ma plus mb divided by mb times cosine of theta. Okay, and that is the answer to part A. Okay, so this is going to be what is question 2, but for the way that this is listed, this is for A. The next part, which is going to be for B, we want to find what the maximum value P can have without crushing the box if now the surface of the table is such that there's a coefficient of friction mu between the table and the first box, Ma, but the rest of it is going to be frictionless. So to do that portion, all we need to do is we need to look at this right here. So when we're looking at this accelerate, the sum of the forces in the x direction for the first block A, there's going to be an additional term here because there's going to be a force of friction. So this is going to say that this is going to be Ma Ax is going to be equal to P cosine of theta, we still have that component, minus NBA minus, this is going to be minus mu times NA, okay? Where NA is going to be, so this is going to be P cos theta minus NBA minus mu times MAG plus P sine of theta, okay? So let's take this and move it down and use it down here. So let's erase this and then get rid of that. And then we'll stick this down here. So I'm going to just draw a free body diagram to go along with this really quickly, just to show you the modification that we have here. So now for box A, so this is MA, still had our normal force NA. We have the force of gravity, MA times G. We have the applied force, the angle theta, P. We have the force that box B acts on A. But now we also have a force of friction, which is going to be equal to mu times NA. Okay, and that's how I ended up picking up this this next term here. Okay, so all reason why we did this is because this is just going to modify our system of equations, and so just for completeness, let's draw the free body diagram for box B again. So this is going to be MB times G, and this is going to be NA acting on B. Okay, so this is MB. And so in the x direction for, so this is for A, this is for B, and really what I'm saying is that the sum of the forces in the x direction is equal to this, and we're saying the sum of the forces in the x direction is equal to this. So this is going to be MB AX, which is going to be equal to NAB. So again, what we're going to do is we're just going to add these equations together. This ends up saying that MA plus MB times AX is going to be equal to P cosine of theta minus mu times P sine of theta plus MA times G, okay? And then we want to, again, solve this for AX. So AX is going to be equal to 1 over MA plus MB times, I'm going to collect some terms here. So this is going to be P times cosine of theta minus mu sine of theta minus mu MAG. Okay. Now we can take this and we can evaluate again for NAB. So we're going to say that NAB is going to be equal to that critical value that we had before, T sub C, which is also equal to MB times AX. We have what AX is now. So we have our AX, and we just evaluate it for that. So this is going to be equal to MB over MA plus MB times P times cosine theta minus mu times sine of theta minus mu MAG. Okay, so now what we want to do is we want to solve this for P, because we need a condition for P. So this ends up saying that TC, so this is going to be TC times MA plus MB divided by MB plus mu MA times G divided by cosine of theta minus mu sine of theta is equal to P. And that's our final answer for this question. Okay, that was a little bit of algebra in there, so just make sure that you can follow the steps that I went through, but it's not really that bad. And barring any minor mistakes that I had with the algebra, this should be correct. I can look at it and see that at least dimensionally this is correct. Okay, so we'll move on to the next one. All right, so the next problem is going to be this problem with this set of blocks on this inclined plane right here, where the mass M2 is going to be stacked on top of the mass M1. M1 is going to slide down the plane, M2 is going to be pulled up the plane, and we ultimately want to find a condition for the coefficient of friction so that this is going to stay at rest. So first thing that we always do with these kinds of problems, we draw a free body diagram. So this is going to be mass M1. This is actually a capital M, so this is going to be capital M1. Then we have our mass M2. So mass M1 has the force of gravity acting down, so this is going to be M1G. We have some normal force, we'll call this N1, because this is the normal force from the inclined plane acting on N1. We also have a normal force that is acting from block 2 to block 1. So we're going to call this one N21. We have the tension acting up, and we also have a force of friction, and we're going to call this F. That is the force of friction that object 2 acts on object 1 to prevent this from moving. Okay. Then when we're looking at mass M2, we have the force of gravity. This is going to be M2G. We have the normal force N12. So this is going to be the normal force that block 1 acts on block 2. We have the tension T, and we have the force of friction that block 1 acts on block 2. So this is going to be F12. And this is going to be opposing the direction of motion. And so we can see that there is a set of forces, or two sets of forces, that connect block 1 to block 2 via mutual interaction, right? So these are Newton's third law pairs. So we have one that comes from friction. So there's force of friction. You can see that these are going to be equal and opposite. So I'm going to underline this so I'm not blocking my indices. And we also have the normal forces. So we have the normal force that block 2 acts on block 1, and the normal force that block 1 acts on block 2. So we can draw a coordinate system here. So I'm going to say that this is the coordinate system for block 2, and this is the coordinate system for block 1. So the reason why I'm using different coordinate systems here is because the direction these are going to move are going to be opposite, right? So block 2 is going to go up the plane, and block 1 is going to be going down the plane. So I drew my coordinate systems to reflect that. Okay, so let's look at how we're going to sum our forces for M1. Okay, so we can write general Newton's second law, sum of forces is equal to mass. This is going to be a capital M1 times a vector. Sum of forces in the y direction is going to be equal to M1 AY. This is going to be 0 because it's not going to accelerate in the y direction. So this is going to be, we can draw our angle here, theta. So here's our angle of theta. There's our angle theta. So make that a better theta. So there's our angle theta. And this right here is going to be the angle of theta. Okay? So that says then in the y direction, we have N1. This is going to be minus N21 minus M1g times cosine of theta. And this is going to be equal to 0. So this says that N1 is going to be equal to N21 plus capital M1g times cosine of theta. Okay? So the next equation that we can get here for M1 comes from the sum of forces in the x direction. So sum of forces in the x direction is going to be equal to M1 AX. So this is not going to be 0 because we're going to have some acceleration here in general. So this acceleration is going to be equal to M1 times g times sine of theta, right, minus t minus f21. Okay? So now we want to do the same thing for block M2. So for block M2, sum of forces in y. So you'll notice that a lot of times here I end up doing the sum of forces in y first because it ends up being useful information for the sum of forces in x, right? So have this one. That's why I looked at this one first. So I tend to actually do the sum of forces in the y direction first. So this is going to be M2AY, which we know is going to be 0. This is equal to, from our free body diagram, we see that this is going to be N12 minus M2g times cosine of theta is equal to 0. So we can draw this in here so we can see that there's the angle theta, and this is going to be M2g cosine of theta. That's why I have that there. Okay. So from this one, we can see that N12 is going to be equal to M2g times cosine of theta. Okay. Now, this was useful information because ultimately this is going to be related to our force of friction if these things are moving. Okay. So now what we're going to do is we're going to sum our forces in the x direction. So sum of forces in the x direction is going to be M2 times AX, which is going to be equal to, this is going to be equal to, now we have to be careful here because we changed the direction of our coordinate system. You see how this is going this way now? So positive tension minus M2g times sine of theta minus the force of friction F12. Okay, so you see how we changed our direction for our coordinate system? So this is what we have. Okay, so now let's write down some of the things that we know here. And so actually, what we end up seeing combining these two equations is that N1 is going to be equal to M2, or we can do it like this. So this is going to be M1 plus M2 times G times cosine of theta. So there's our normal force N1. We have our normal force N12. So this is going to be equal to M2G cosine of theta. Okay, so summarizing the useful information here. And then we have the equations from our sum of forces in x. So this is going to be M1AX is going to be equal to M1G sine of theta minus T minus F21 and then m2 ax, because we're going to say these have the same acceleration, right? The string is a fixed length, so they're not accelerating relative to each other. They're keeping constant distance along the string. So these have the same acceleration, and this is going to be equal to t minus m2g sine of theta minus f12. Okay. Now here we see something kind of interesting, because when we add these together, our tensions are going to cancel, but our force of friction isn't. And this is actually really important, because what we end up seeing here is we have capital M1 plus M2 times AX is going to be equal to, this is going to be capital M1 minus M2 times G times sine of theta minus F12 times 2, right? Because as a magnitude, F21 is equal to F12, right? And so I just combined these two terms right here, because these are the same thing. But they're not canceling. We got double the friction here that's opposing this, which is kind of interesting. And so in order to get this fully parameterized, what we need to do is we need to replace F12 with mu times N12. But we know what N12 is. We found it here already. So that's that. And so I'm just going to do a little bit of algebra in one step here, just to save a little bit of time. And so what we end up seeing is that the acceleration is going to be m minus m1 minus m2 times g times sine of theta minus 2 times mu times m2g cosine of theta divided by capital M1 plus M2. Okay, so that's our acceleration. Okay, now the last thing that we want to do is we want to determine what the condition is for the coefficient of friction for these blocks to remain at rest. And so that's just to say that this acceleration, a sub x, is equal to 0. So we say 0, 0. Okay, let's write this in, what happened? So 0, 0 is equal to m minus m2 g sine of theta minus 2 mu m2 g cosine of theta divided by m1 plus m2. We can get rid of our denominator here, right? Because that doesn't have any condition on this. And then we can solve this for mu. And so when we solve this for mu, we end up seeing that this is going to be equal to capital M1 minus M2. Our g's are going to cancel. We end up having a sine of theta divided by cosine of theta, which is a tangent of theta. And then this is going to be divided by M2, and there's a factor of 2 in the denominator here. Okay, so that's going to be it for this question. Okay, let's move on to the next question.